Hello everyone and welcome to the Advanced Manufacturing Lab here at the University of Guelph. My name is Graham and I'm a graduate student in mechanical engineering. Today's video we're going to do a demonstration of the use of a vertical mill CNC machine. Today we'll be using the Haas VF2 shown behind me. This machine is equipped with automatic probing, has a 20 horsepower motor and goes up to 8,000 RPM. Today we're going to be creating the Titan 1M. This is taken from Titans of CNC Academy. The first thing we're going to go over is how to power up the machine. It's pretty straightforward. We're going to start with the green power on button and we should see the screen come to life. This process takes about 30 seconds for the machine to initialize, so we're going to fast forward through it. Once the machine has come to life, we see we have some on-screen instructions and our light is flashing red, indicating we have an alarm. First thing we're going to do is reset our emergency stop by twisting clockwise and pulling out. Then we're going to hit reset to clear our alarms. Once we've done this and there are no alarms flashing, we're going to go ahead and hit power up. This is going to get the machine to zero out all three of its axes and switch to its home tool, in this case tool number 1. It's important to note we need the doors to be closed in order for the machine to power up. To change tools, we're going to select Manual Data Input, or MDI, from our mode button. We're then going to type in the tool number we'd like, so T for tool. I'm going to use 3 as an example, and then we're going to hit ATC, or automatic tool change, either forward or reverse. Forward rotates in the direction that has the least steps, reverse goes the other way. This can be important if we need to avoid running a tool in the carousel into our workpiece. To remove a tool from the machine, first we need to make sure we're wearing our safety glasses because sometimes we get a coolant spray when we release it. Next we're going to find this button and holding our tool like an ice cream cone, we're going to press this button and the tool drops out. You'll see that the tool holder has 2 grooves. These line up with corresponding grooves in the spindle. To put the tool back in, we again hold the tool like an ice cream cone. We're going to put this tool into the spindle, ensuring that our hands are clear, and we press the button again, and the tool goes up. Next, we're going to look at setting up our piece for our operations. You'll see that we have our vise mounted on the table. We also have our parallels. These are a ground set that sit on the base of the vise, and they ensure our piece is held square. First thing, we're going to take a clean rag and we're going to wipe out our vise as well as wipe the bottom and top of our parallels. This ensures that there's no particles or chips sitting under them, so our piece will sit flat. Next, we're going to take our stock and we are going to place our stock in the vise. We then use our vise handle, which we keep beside the vise, or beside the machine, to tighten up slightly. And we use our rubber mallet to make sure the piece is secure. We want to double check our parallels. If they slide a little, we just want to give them another tap and make sure they're secure. Next, we're going to look at using our automatic probing system to set our work offsets. First thing we're going to do is call up our spindle probe, which is tool 20. We're going to go MDI, T20, automatic tool change. Next, we're going to handle jog our probe down so that it is over our workpiece. For this part, I have set the origin to be in the middle of the part in the X and Y direction and on the top surface for the Z direction. We want to take our time when we get close to the piece to make sure we aren't bumping the probe into the workspace. Next, we're going to choose one of the canned probing cycles in the machine. To do this, we're going to go MDI, program, and now we have an option here to choose spindle probe, several spindle probe options. First, we're going to probe the Z surface, so we're going to choose enter, drop down, probe Z surface, and enter again. The machine now asks us for the work offset. We're working with G54, so we're going to type in 54, enter. It asks us where we want the output to go, and we're going to choose output to MDI. We hit enter again. We now have our code copied into the MDI, so we're going to hit MDI, our code turns white, and we're going to hit cycle start. Once we've probed in the Z direction, next we're going to go back to the MDI program spindle probe options, and we're going to choose from the second menu our X web program. What this is going to do is probe on one side of the X, probe the other side of the X, and give us the origin at the exact center of our stock. We hit enter. We're going to choose our work offset again to be 54. Our width is the width of our part, so we're going to hit 4. And depth, this is a negative value, and this is how far we want the probe to drop down before it probes back in. We're going to put negative 0.5, enter, and again we want output to MDI. Finally, we're going to repeat this process to probe in the Y direction. Again, we want to find the center of the stock, so we're going to go MDI, program. From our second spindle probe menu, we're going to choose the Y web, and this is the same procedure as before. We're going to type 54, our width is 2, and our depth is going to be negative 0.5, enter. Again, we want our output to MDI, and we have our code. Similarly to when we were running a probing cycle with the spindle probe, to run the tool probe, we're going to go MDI, program, and we're going to choose tool setting from our menu. We're going to hit enter, and we have several options. Automatic length only will run the tool down, straight down into the probe and then back up. This is great for tools that have a single point, but not great for face mills or end mills where we're concerned about the outer cutting edge rather than the center. For face mills and end mills, we're going to use automatic length rotating. This will run the tool backwards, allowing us to skim the top of the probe without cutting it. It also offsets the tool from the probe, so the outer cutting edge is what is hitting the probe base. Selecting a program is straightforward. We use our USB port on the side to input a USB. We then go select program in our menu option. We have two choices here. We either have memory, which is the computer's internal memory, or we have our USB device. To toggle between, we hit cancel, toggle over, enter, and now we can select our program from this list. Having selected the program, we can now simulate this program on the machine to make sure that our tool numbers are correct and we aren't asking the machine or the bed to go beyond its capabilities. We're going to come to the display section and we're going to hit settings twice. This brings up this screen, and if we go ahead and hit the cycle start button, we'll see the machine simulate our program on the screen.
It's important to note that this simulation won't tell us if the tool offsets are done correctly or how deep the tool is going to go, but it does show us which tool is being used, what the general tool path looks like, and that our work will fit in the workspace of the machine.
Before we start our program, it's important to look at our override section here. We have overrides for our feed rate, our spindle, and our rapid setting. Feed rate and spindle are both set in our programming software, so ideally we set those correctly the first time. However, if we need to, we can override them both up and down. It's important to keep in mind that these overrides will not automatically reset when an operation finishes and another one begins. So if we are using these, we need to keep an eye on them to make sure that we aren't ignoring them or setting the wrong speed for subsequent operations. Rapid is the speed the machine moves at between operations, whether that's moving the table bed or changing tools.
Here we have our facing operation. We're running one pass with a 2-inch face mill. We're running at 6,000 RPM and 60 inches per minute, which is 2 thousandths per tooth. And we're running at a depth of cut of 50 thousandths. Normally we would run coolant, but we turned it off so we could see the operation better. Next we're going to create the pocket in the middle of the part. We're going to do this using a 4-flute carbide 1/2-inch end mill. First we're going to helically bore down into the part. We're going to do this at a 2-degree ramp, running the tool at 32 inches per minute and 8,000 RPM. The tool is going to bore down in a diameter of just under 1 inch so that all the material within that bore is cleared. Normally we would run coolant to promote chip evacuation, but again we chose not to make this more visible. Helically boring is not the easiest on tools, particularly flat bottom end mills. If we were running high production, it might make more sense to drill a hole and allow the tool to drop down before we did this, but for one part this is the quickest way to get down. Now we're going to remove the rest of the material from the pocket. We're going to bump up our speed to 64 inches per minute while keeping the 8,000 RPM going. We're going to keep the tool at full depth, so we're taking 0.6 inch axial cuts, but we're only going to step over 0.1 of an inch each time. When the tool is not engaged, Mastercam automatically programs it to run at 100 inches per minute till its next engagement. When we were hollowing out the pocket, we left 5 thousandths of an inch on the edge. This was so we could come back with the same end mill and do a contour pass around the whole perimeter to give us a nice smooth finish. You'll see that there's pretty significant buildup of chips, and this would have been cleared had we run coolant, but we kept it off. In this operation, we definitely regret having that coolant off because, as you might see, or you'll see from the finish, we end up recutting chips, which ruins our surface finish in some parts. We're now going to follow the same procedure to shape the outside of the part. We're going to start with full depth of cut and minimal step over, and then we're going to come back and finish it with a contour pass. We're going to run the same speeds and feeds, and again we should be running coolant, but we have it off for visibility. Here we are going to change tools from the 1/2-inch end mill to the 1/4-inch chamfer mill. The chamfer mill is great because it allows us to deburr the part while it's still in the machine. It also allows us to start our holes for the drilling operations. You'll also see that I blow off the part. This I should have done before we contoured, but this is just to clear the chips. The chamfer mill is running at 8,000 RPM and 16 inches per minute. It's taking a 25 thousandths chamfer on both the inside and outside perimeter of the part. Now we're going to use the chamfer mill to spot our holes for the drilling operations. For these, the chamfer mill is going to go at 6,000 RPM and 8 inches per minute plunge rate. Now we're going to see a tool change from our chamfer mill to our 136 thou drill. For this operation, we're going to drill at 6,500 RPM and a plunge rate of 8 inches per minute again. We're going to peck drill here, so the drill is going to go down in steps of 0.1 inches, and this is to facilitate chip breakup so we don't end up with a bird's nest on the drill. Our final operation will be a tapping cycle to tap the 7 holes on the part. We're using a 1032 tap and the canned rigid tapping cycle from the Haas machine. In this program, we're going to run at 1,000 RPM, and you'll see the tap will spin down, pause at the bottom, and then spin back in the reverse direction.